Hi, my name is Ruben Heradio and I'm going to present the paper Uniform and Scalable Subsampling for Configurable Systems. Let's start motivating our work. Why do we need uniform random sampling? Well, answering many relevant questions would be really easy if we could perform an exhaustive analysis of all valid configurations in a software product line. However, in most cases, this is unfeasible. Let's see why with an example. There is a software tool called Busybox that provides highly customized environments for embedded systems. To do so, it supports the inclusion and exclusion of optional features at compile time. Features are specified with the kconfig language. In particular, every feature is encoded as a config. For example, here we can see that there is a feature called static, another one called pi, and so on. With the kconfig language, we also specified dependencies between features. For example, this one says that pi and static are mutually exclusive. Constraints conformance is typically validated with logic engines, such as SAT solvers and binary decision diagrams, BDDs for short. For that, the kconfig specification needs to be translated into a Boolean formula. This graph represents the whole kconfig specification of Busybox. Nodes account for features and links for feature dependencies. For example, here we can see the static and pi feature, and this line represents their mutually exclusive dependency. Although this graph seems very complex and a little intimidating, in fact, Busybox is a modest example with not many features nor constraints. However, its space of valid configurations is huge. There are this huge number of valid configurations, and that's why we cannot perform an exhaustive analysis of all of them. And that's why we need to use an alternative approach when we want to target many interesting questions. Another takeaway of this example is that this space of valid configurations is only a tiny portion of the whole space of possible configurations, that is, of configurations without considering the feature interdependencies. A promising alternative approach to the exhaustive analysis of all valid configurations is the statistical inference. In this case, instead of working with the whole population of valid configurations, we are going to work with a sample of a few configurations. Then we will make inference, that is, we will try to generalize the sample results to the population. In statistics, a sample is a collection of cases, and the sample size is the number of cases in the sample. So, in this presentation, a sample is going to be a set of configurations, and the sample size is going to be the number of configurations in the sample. Inference works whenever the sample is representative of the population. And a mandatory requirement for this is that the sampling process needs to be uniform. Uniformity means that each member of the population must be equally likely to be included in the sample. In other words, if the population has n valid configurations, the probability every configuration has to be included in the sample is 1 divided by n. A naive approach to build a uniform random sampler would be to start ignoring the interfeature dependencies. So we could just generate random configurations and then use a SAT solver to filter only those configurations that are valid. This sampler will be uniform but not scalable, because remember that the proportion of valid configurations is tiny. This means that we will need to generate many possible configurations until we reach a valid one. So uniformity is not enough. We also need scalability. Nowadays there are several samplers that claim to be both uniform and scalable. However, their uniformity hasn't been validated properly yet. Several uniformity validation methods have been proposed, but they have important shortcomings. First, they require huge sample sizes to produce reliable results. For example, the most popular method in the literature needs a sample of 4 million configurations to test a small model with less than 300 variables. As a consequence, samplers' uniformity has been checked only on miniature models so far, which hinders external validity of the results. Another shortcoming is that most methods only provide a uniformity measure, but not its statistical significance. I'll talk a little more about this in a few slides. So, what's our paper about? Well, in our paper we propose a new method to verify samplers' uniformity which overcomes the shortcomings I just mentioned. We also apply this new method to validate the uniformity and scalability of 4 state-of-the-art samplers, which are SPUR, Quick Sampler, Unigen2, and SMART. This figure represents our method to validate the uniformity of a sampler. To do so, it compares empirical information of a sample generated with the sampler with theoretical information regarding all valid configurations in a software product line. In particular, we apply a goodness of fit test to compare variable frequency distribution with variable probability distribution. In other words, for each feature, we compare its probability with its frequency. Feature probability is the number of valid configurations, including the feature, divided by the total number of valid configurations. Feature frequency is the empirical equivalent to probability, and it's the number of configurations in the sample, including the feature, divided by the sample size. Whereas computing feature frequency is trivial, it's just a matter of counting, computing feature probability is another story. This is typically performed by calling repeatedly a Sharp solver, in particular once per feature. Unfortunately, this procedure is extremely expensive, it takes a long time, and that's why we in our paper use another approach based on VDDs. We presented this approach last year in the ICSI conference. To compare the empirical frequencies with the theoretical probabilities, we use the Jensen-Shannon divergence, which ranges from 0 to 1. 0 when there is no divergence at all, that is, when the frequencies and the probabilities match perfectly, and 1 when the divergence is total. It's worth noting that the divergence completely depends on the sample. If we ask the sampler to generate a new sample, we will get a new divergence. And that's why having a particular divergence is not enough. We need to know how representative is this divergence. That is, how this divergence changes from sample to sample. In other words, we need to know what's the statistical significance of this divergence. This means to convert the divergence into a p-value. Fortunately, this can be done because this expression here follows a chi-square distribution. Accordingly, sampler's uniformity can be validated by performing a standard chi-square goodness of fit test, whose null hypothesis is that the sampler is indeed uniform, in other words, that the sample agrees with the population. This density plot shows for a particular variability model how this expression distributes assuming that the null hypothesis is true. If for our sample we get a value that is here in the tail, its probability is going to be very low. This means that the sample is not coherent with the null hypothesis, and so we will reject the null hypothesis. That is, we will reject sampler's uniformity. Finally, we will take advantage that in goodness of fit test is well known that the minimal sample size can be determined for 3 parameters, which are the type 1 and type 2 errors and the effect size. Let's review the results of our empirical evaluation. We use a benchmark composed of more than 200 models, ranging from small ones to very large ones with more than 70,000 features and 300,000 clauses. Remember that existing validation methods require huge sample sizes with millions of configurations. This histogram shows the sample sizes required to validate the uniformity of the samplers in all the models in the benchmark. We have used these high precision parameters, that is, the probability of making a type 1 error is just 1% and a type 2 error is again just 1%, and effect size is 0.1, which means very high sensitivity for our test. Even with those parameters, in most cases, we just need a few thousand of configurations to validate the sampler's uniformity. For the largest model, we are below 100,000 features instead of millions. This histogram shows the time required to compute variable probabilities. In most cases, a few seconds were enough, and for the largest models we needed about 8 minutes. In other words, our validation method scales in terms of sample size and time efficiency. Regarding sampler scalability, we ask the samplers to generate each sample within an hour. Spur and Quick Sample were able to generate almost 100% of all samples within the timeout. However, Unigen 2 and Smart failed. This plot shows how the sample generation time depends on the variability model size in terms of number of features. Unigen 2 and Smart were unable to generate the samples for models with more than 300 features. Regarding samplers' uniformity, these histograms show the p-values each sampler obtained, where in most cases Spur, Unigen 2 and Smart got p-values close to 1. This is not the case for Quick Sampler. Most of its p-values are close to 0, and a few ones are close to 1. These few ones corresponds to models with less than 150 features. To sum up, whereas Spur, Unigen 2 and Smart warranty uniformity for every model in the benchmark, Quick Sampler only satisfies uniformity for the smallest models. The main conclusion of our work is that out there is a sampler called Spur, which is both uniform and scalable. So the software product line community is ready to go for the statistical inference approach.